So why so extreme, Maha? Extrema on an interval. So today we're going to find extrema on an interval, a closed interval in particular. We'll be successful when we can use derivatives to help find extrema on an interval. And we're going to kind of come back and talk about this. That's one of the big things in this chapter. So the big concepts that are new for us are going to be how can we use the derivatives that we've learned how to find? That's really what this chapter really is about. Like technically we did a little bit with related rates. Like that's a really awesome application. It doesn't always, not everything works out very well all the time with that, but there's some very simple situations where you can use that to model things really, really well. Anyways, extrema is a minimum or a maximum. But how do derivatives help us with that? So we're going to kind of look at that and think about that a little bit. So here's what I like to do is give you like 2 minutes. I want you to just look at this graph and just kind of on your own sheet of paper, identify all the extrema you can find. So decide whether they're global or absolute. Sometimes we call global extrema also absolute extrema. And that's the terminology I'm going to use most of this class, but I like using global as well. Determine whether things are maximums or minimums, and think about what is the sign of the derivative, not the value, but the sign of it at that particular point. So I'm going to give you 2 minutes. And go. Again, just kind of look at it, record those X values on your paper. Do. All right. Let's take a look and see how you did there, folks. So here's a slightly bigger graph so we can kind of look and see kind of what's going on. Here, there should have been 1, 2, 3, 4, 5 points you identified. Bam. X equals 0, X equals 0.7, X equals 1.5, X equals 2, and X equals 2.5. So looking at these, we have 2 global minimums at X equals 0 and 2.5. We have a global max at 0.7. And then there's a local min and a local max at 1.5 and 2, respectively. So looking at the slope at the 3 in the middles, like the end and the beginning are technically those are extremums, like their highest or lowest values. But if we look at the pieces in the graph, the global max, the local min, the local max, if we draw in the derivative of each of those, it's 0, right? There's a horizontal tangent line at those spots. Down here, technically the derivative doesn't exist there because it's not continuous at that point. And if it's not continuous, it can't have a derivative. And we'll talk about that a little more later. Again, same thing over here. The derivative doesn't exist. But I mean, after it's negative, or after it's positive, before this one's negative. So it kind of still fits with the idea of global min, and we'll talk about more along with that later. But I really want to look at these three right there. The derivative 0, where these extrema, not at the edges of the graph, occur. So whenever the derivative is 0, do we have extrema? Not always, because see this horizontal line? This is neither extrema, this is not an extrema. But the derivative is 0 all along this graph, which is a really interesting thing to think about. At the post credits, I linked an explanation from a mathematician about why a horizontal line isn't a max or a min or both. Well, I mean, just to find out more about if it's extreme or not, there's some stuff in the post credits about that. So I want to give you that. It's not a super important thing for what we're talking about, but I still want to mention that that's there. So here's a super important thing for you. A critical point is when the derivative is 0 or undefined. Or to put it in kind of our math terminology, our symbols, f prime of c equals 0, or f prime of c is undefined, where c is a critical point. So local extrema only happen at critical points. So that if we go back, this global max is also a local max because right around it, there's nothing bigger than it. And the function still exists kind of around it. So local extrema only happen at critical points, but not all critical points are local extrema. So that's something we're going to start looking at and thinking about. Now, the big thing you're going to use here is looking for and using critical points. All right. So there's a value theorem that we're going to use. There's a value theorem we had looked at in last chapter. It's called the intermediate value theorem. It's that if you have a continuous function, every output between the two endpoints must be attained at least once. Extreme value theorem says something different. It's a value theorem. There's 3 value theorems that we use in calculus. This is the second one. They're all very important, so it's important that you take a minute to think about and look at this. So extreme value goes like this. If f is continuous on a closed interval AB, meaning we include the 2 endpoints, then f has at least one minimum and at least one maximum. All right. So here's the general prompt that I'm going to give you with something like that, like go along with the extreme value theorem. Find all absolute extrema for the given functions on the given intervals, or given function on the given interval. All right. So let's take a look at that. So I would recommend writing this down as we go along together. Just again, it's a little bit of that muscle memory aspect. Yeah, I would recommend that. Anyways, so we have this function, y equals 1/3 x to the third plus 5/2 x squared plus 6x plus 5 on the closed interval -5 to 0. I wrote it using interval notation because I used Desmos to write this because I was lazy and I didn't want to go use Equatio to do it. So, and Desmos does stuff in LaTeX, so that works for me. So here we go. So I want to find the absolute extrema for the given functions on the given interval. So this is the given function I have. Well, noting that the global max could be a local max, or a global extrema could be a local extrema. So we need to find some critical points in order to start checking everything. So we need the derivative of this. So we're going to take the derivative of everything with respect to x. When we do that, well, the derivative of y with respect to x is just going to be dy dx. The derivative of this bad boy over here is going to be x squared plus 5x plus 6. So now that we have a derivative, we want to figure out when is that derivative equal to 0 so we can find the critical points. So set it equal to 0, and we can go from there. Noticing it's a quadratic means we might be able to factor that some good. So let's try that. And it does. It factors into x plus 2, x plus 3. Now, before I go any further, I feel like I kind of blew through a couple steps. What questions do you have that you're feeling brave enough to ask at the moment?
How did you get from like 2 to 3?
2 to 3? Got it.
Yeah.
So in 2, d dx is saying we are going to take the derivative of y with respect to x, and then we're going to take the derivative of this side with respect to x. So from 2 to 3 on the left-hand side, I just did the derivative of y with respect to x, which using everything that we did in 2.5 and 2.6 and what we've kind of did before but didn't say, this is just the derivative. I'm sorry, let me point using this. dy dx is just the derivative of y with respect to x. So we did the derivative there. Technically, it's like 1 times dy dx, but we've never really like kept focusing on that. We just said dy dx. And then we did the derivative over here of each of these things using, since these are all polynomial, this is a polynomial, we can just use a power rule on each of these. So 1/3 times 3 is 1. Take 1 away from 3 is 2, so we get x squared. Multiply 5/2 by 2 to get 5, and take 1 away from that, we get 5x. Derivative of 6x is 6. The derivative of 5 is 0. That's how we got there. Does that help?
Yes, thank you.
You're welcome. Thank you so much for asking that question. What other questions do you have before we move on to the next part? Okay. So now that we have this factored, we can finish solving this to determine what our critical points are. And we get x equals -2 and x equals -3. Now, since we're looking for absolute extrema, there's the next thing we're going to do is a thing we're going to do pretty much every time. What I want to do is I'm going to list out the endpoints and every critical points. Boom. So -5 and 0 are my endpoints. -3 and -2 are my critical points. So they could be they could be a max or a min. They might not be, but they could be. I can show you an example later of where you have a critical point, but it's not a extrema. So now what we're going to do is, this is actually simpler than you think. We're going to take each x value and plug it back into the original equation. The reason we're doing this is we're going to just numerically compare the outputs of these 4 inputs and see which one's the biggest and which one's the smallest. And that's it when we're looking for absolute value or absolute extrema. So let's do that. We plug in -5. We get y equals -4.167. By the way, I'm pretty confident in a quarter of calculus that I haven't mentioned this, and I need to mention it now. When you're doing any decimal approximations in calculus, I mentioned a lot in pre-calc, but I haven't mentioned it yet in this class. You need at least 3 decimal places. Okay? You need to be accurate to 3 decimal places. So that means you could have 4, 5, 6. That's fine. A lot of the AP rubric stuff that we'll look at later in this course when we do even more AP free response practice, and you see the answers, they'll have answers to like 7 or 8 decimal places just to make sure. But you only need 3. and you can round or truncate, meaning like if this was 1 point or 0.1666 repeating. So your answer could be either negative 4.167 or negative 4.166. Either one's fine. All right, let's plug in -3. Again, these y values are not from the derivative. They're from the original function. They're the y values. I take -3 and plug it in up here. I get 0.5. I take -2 and plug it in up here. I get 0.333 repeating. So this is -4 1/6. This is positive 1/3, positive 1/2. Now let's plug in 0 to this, and I get 5. So I want to determine what's my absolute minimum, what's my absolute maximum. Well, absolute minimum is literally just the smallest output, which is -4.167. And my absolute maximum is 5. The critical points, we didn't need them. And I mean, neither one of them were the absolute min max. And we don't always know that if they're going to be or not, but you always need to check for them. I mentioned that because in the free response of the AP test, there are points for determining these values, coming up with the critical points. Like even if even if they're not absolute extrema, you still get points for finding them. So that's why it's so important you look for them all the time, because that's like the big skill here. The big skill here is taking the derivative, finding the critical points, then testing the endpoints and the critical points to see which have the largest and smallest y values. All right, we should algebraically work that out every time. Can you graph to check it? Sure, that's fine. There's nothing wrong with that, but don't rely on this because the wrong scale might mess with you. Especially if you're looking for critical points, you might not see the critical points on the graph. But look at that graph. Note on that graph, you can see -5 definitely give us the output of -4.16, and that's an absolute minimum here. And that's absolute max. Looking at these points though, this first critical point, both critical points were actually local extrema. -3 was a local max, -2 was a local min. So that's interesting. So again, algebraically work it out every time, and you can graph to check, and that's fine. And by the way, again, in Desmos, if you just graph or literally type this in, that's how I got this graph. I just type this in with the domain restriction, and it shows up. All right. There's your local max. There's your local min. I forgot to put those in there. So make sure you do those things because all right. So I want to find all absolute extrema for the given functions and the given intervals. I'm not going to have you actually like go there. I would like for you to try to do these on your own at a future time, but I want to show you what the answers are so we can talk about some different things on them. Like if I took the derivative of this, I get x squared minus 1, which is going to give me plus or minus -1 for critical values. So -2, -1, 1, and 3 are the x values you need to check and plug back into the function, the original function, to find out which are the biggest and smallest values. So let's do that. And I'm just showing you the graph just to point this out. There's our graph. And here's the graph for sine of x from 0 to 5/4 or 5 pi over 4. And again, derivative sines cosine. Cosine's critical point from 0 to that is pi over 2, which you can see right there. So again, if we're trying to identify some absolute minimums, notice again that this first one, the endpoint is an absolute minimum, as well as one of the critical points. which is part of the reason you always need to check them, because you're never going to be sure until you algebraically check it and figure it out. Then again, graph will help you. Don't rely on the graph. That's your check. Okay, it's a check, but it shouldn't be your first step. If it's your first step, you're missing the algebraic point of the lesson. Okay. And over here, we can see 5/4 pi, 5 pi, 5/4 pi is our absolute min. And there is our absolute maxes. For this first one, again, the endpoint was my absolute maximum. But for sine of x on this interval, the critical point was the absolute max. So you got to be careful. Look at those things, be careful. Always make sure to check the endpoints and critical points for those absolute extrema, because both of these, while they're a little bit different, they each have the issue where one of the absolute extrema is at a critical point. So you need to check the endpoints and the extrema, or the critical points. The critical points are when the derivative is 0 or undefined. This is the way. That's it. Ish. So if you have your graphing calculator and you want to learn how to do more of it with your graphing calculator, there's 2 links for you. The first one is a link to the 4 things that you're allowed to not justify on the AP test using your graphing calculator. Your graphing calculator, and so you can work with that. I don't know if it's going to be all digital or not this year, or if it's going to be online, or if it's going to be in person. From the emails I've got from AP personally, I think it's going to be online again, which is kind of sucky, but it's kind of good. It's kind of everything. So just be aware. Or the second link is just a general list of things you can do on your graphing calculator that maybe you didn't know. It's a thing that I've put together. If there's something on there you'd like improved or something you'd like added, or let me know and I can fix that and change that. Here you go. Here's your practice. It's due soon. In Schoology, I think I said the due date was, I think I said Thursday. I don't know. Sometime this quarter. You should work on it, get it done soon. There's also some post-credit scenes. Again, post-credit scenes just are some extra little stuff for you that I would recommend taking some time to look at. That's what I have. I'm trying to think if I had anything else, but I think that's pretty much it. Oh, quiz. You probably want to know what that looks like. Let me grab the numbers real quick. We decided on values yesterday. There you go. So that's going to be the scaling for the scores. I'll hit you up in just a sec. So those are the scores. If you had anything more than an 8, that's also 100. But that's how it's going to kind of look. 6 was half of the points. So that's just kind of how it all worked out. And then one of you have to touch base with about that. All right, let me stop this part. I don't think I need to record.